Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the fifth in a series of short videos on basic electronic circuit analysis. So far I've covered Ohm's law, Kirchhoff's current law, Kirchhoff's voltage law. In the last video I covered a sleight of hand, which was Thevenin's theorem, which produced an equivalent circuit comprised of a single voltage source in series with a single resistance. In this video, I want to cover the companion sleight of hand to the Thevenin equivalent, known as Norton's theorem, which gives us Norton's equivalent circuit. Who was Edward Norton? Well, he was an American, and he was an engineer and scientist at Bell Labs. Norton's theorem was released in 1926. If you find this video helpful, please click on the like and subscribe so that you will be notified when new videos come out. So what does Norton's theorem tell us? Okay, hang on, here we go. For any linear electrical network containing only voltage sources, current sources, and resistances, it can be replaced at terminals A and B by an equivalent combination of a current source, I sub NO, in parallel connection with a resistance, R sub NO. Now we get R sub NO by shorting all voltage sources and opening all current sources, and then calculating the remaining resistance value. This should sound very, very familiar to the Thevenin equivalent resistance. We get I sub NO by calculating the voltage at A and B with them open circuited. Now again, this goes back to Thevenin's equivalent circuit, but then we divide that open circuit voltage by R sub NO, which by the way happens to be the same as R sub TH from the Thevenin equivalent. Now, are you confused by this? Well, I don't blame you. Let's see if we can unravel this whole thing at the whiteboard. So, Norton's theorem. In order to apply Norton's theorem, we have to begin with using Thevenin's theorem. Now, Thevenin's theorem, if you haven't watched the previous video, Thevenin's theorem tells us that our first step is we disconnect our load resistor because it requires points A and B, which is these 2 points here. It requires that to be an open circuit out here. The second step is that we turn all of our voltage sources into a short, and we turn all of our current sources into an open. And then as we're looking in through A and B, we calculate the equivalent resistance of this circuit. And when we do that with this particular circuit, we find the Thevenin resistance is 63.75 ohms. Once that is done, we then remove our short, we reconnect our voltage source, we reconnect our current source, but we leave the load resistor disconnected. This is an open circuit. And now what we want to do is find out what the open circuit voltage at A and B is with this connected like this. Having done that, V Thevenin comes out to be 21.875 volts, open circuit voltage. Now, Norton's theorem tells us that R Norton is equal to R Thevenin. So we're just going to write up here R Norton is equal to R Thevenin, 63.75 ohms. Next, we are looking to replace all this stuff with a current source. Our goal is to end up with a current source, I Norton in parallel with a resistor R Norton, and here's our points A and point B. And that's what our goal is. Well, I Norton is equal to V Thevenin divided by R Thevenin. So this is 21.875 volts divided by 63.75 ohms. So we discover then, when we do this simple math, that I Norton is equal to 0.343, if I remember right, 1414 amps. So we're right up here. I Norton is equal to 0.34314 amps. All right, so we'll take this out of the way. And so now we're going to ask the question, what is the current through this resistor and what is the voltage across A and B? And to do that, we add our resistor back in place here, which is 50 ohms. The Norton resistance is 63.75 ohms. This current over here is 0.34314 amps. And when we do that, the thing that we see here are two resistors in parallel. And there's two ways we can do this. To calculate the current across this using the current divider formula, or we can look at this as an equivalent resistance, 63.75 ohms in parallel with 50 ohms. So we have 63.75 ohms in parallel with 50 ohms. And so that gives us 28.022 ohms. Equivalent resistance when you do the math there. All right, so what is the voltage across this point? Well, we have this much current across being shoved through this much ohmage. So voltage is equal to the current times the ohms. So that means that VAB is going to be equal to this current, 0.34314, and we're going to multiply that by 28.022 ohms. And what do we get? 9.615 volts. So VRL is equal to 9.615 volts. Okay, so what's the current through the resistor? Well, the current through this load resistor is this voltage, which appears across it, 9.615 divided by 50, which is the number of ohms, and that comes out to be 0.19231 amps. So IRL is equal to 0.19231 amps. Wow. Now, if you happen to have watched the video on Thevenin's theorem, these numbers are going to look really familiar. So here we are again. We're going to go back through and we're going to verify that we're correct. So that means we reconnect this. The voltage across here from A to B is the 9.615 volts. The current going through here is 0.19231 amps. If we know the current going through here, we can calculate the voltage across here. This is our point C over here. So R2 is 60 ohms. So VR2 is equal to 0.19231. That's the current through it, times 60. And so that gives us 11.539 volts. Okay, so if that's 11.539 volts, and this is 9.615 volts, VC is going to be equal to VRL, or this voltage out here, 9.615, plus VR2, which is 11.539, which is going to give us 21.154 volts. So now we know the voltage at this point. We now can calculate the current through R3. So IR3 is equal to this voltage, which is 21.154, divided by its resistance, which is 5 ohms. So 21.154 divided by 5 gives us 4.2308 amps. Now the current leaving here is equal to the current through here plus the current going out this way. So this current right here, we'll call that I3. I3 is going to be equal to this current, 4.2308, plus this current, 0.19231, which is going to give us 4.42311 amps. Now, 2.5 amps of that is being supplied by this current source. So we know that IR1 is going to be equal to this, 4.42311 minus the 2.5. And that gives us a total of 1.92311, 1.92311 amps going through R1. If we know the current through R1 and we know the resistance of R1, we can say the voltage of R1 is equal to this current, 1.92311, times the resistance, which is 15. So VR1 is equal to 28.84665 volts. So that's the voltage across R1. Well, we know the voltage on this side. We know the voltage across that. So we can say that V1 should equal VC plus VR1. Well, what's VC? We had that here, 21,154 plus VR1, 28.84665. Let's add those up here. We got 5, we got 6, we got 10. 1 and 5 is 6. We got 10. 1, that's 2, that's 10. 1, that's 2, that's 10. 1, 2, 4, 5 that's 50.00065 volts. Yep, Norton's theorem works. So there you have the short and sweet of Norton's theorem, which gives us the Norton equivalent, the companion to the Thevenin equivalent. These two sleight of hand tricks can really help us break down a very complex circuit into manageable pieces. It's one of those circuit analysis tricks that we may not understand why it works, but we do it because it does work. Now, if you found this video helpful, be sure to click on like and subscribe to this channel. In the meanwhile, thanks for watching. Until next time, toodaloots.